Welcome to the video on the basics of C programming, presented by Sheikh Naeem. Before C, influential languages included Algool, which introduced structured programming but was complex. Corporal was designed for system programming but was too large and difficult to implement. Further influences include BCPL, a simplified version of Corporal, and the B language, derived from BCPL and used for early Unix versions. Both BCPL and B lacked data types, limiting their usability. Low-level languages are close to machine code and require direct hardware management. High-level languages are more abstract and easier for human reading. C is considered a middle-level language, balancing both. C was developed by Dennis Ritchie in 1972 at Bell Labs as an improvement over the B language. It aimed to write system software, like the Unix operating system, efficiently and portably. Rewriting Unix in C in 1973 was revolutionary, proving C's power and portability. C is still widely used in operating systems, embedded systems, device drivers, compilers, and game engines. Its popularity stems from portability, efficiency, structured programming, low-level access via pointers, and a rich standard library. C is a simple, structured language where programs are divided into functions, improving readability and maintainability. It is also a middle-level language, supporting both high-level features like loops and low-level features like pointers for hardware interaction. C programs are highly portable and can run on different machines with minimal changes, needing only a compiler. They also feature fast execution and efficiency because the compiler translates code directly into machine language, making it suitable for performance-critical applications. C has a rich set of data types, including basic types like int and float, derived types such as arrays and pointers, and user-defined types like structs and unions. This variety allows for efficient data organization. Pointers are a powerful feature, storing variable addresses. They are crucial for dynamic memory allocation, handling arrays and strings, function arguments by reference, and data structures, providing direct memory control and efficiency. C supports dynamic memory management using functions like malloc, calloc, realloc, and free for efficient memory allocation at runtime. It also boasts a rich standard library with many built-in functions, saving development time. Modularity and reusability are key features, allowing programs to be divided into functions that can be reused, facilitating easier testing and maintenance. C is also extensible, allowing users to create their own libraries and add new features. C supports recursive functions, where a function calls itself, which is useful for problems like factorials and tree traversal. Additionally, it supports bitwise operations, which are essential for low-level programming and hardware control. C is a case-sensitive language, meaning variable and variable are distinct. It has a wide range of applications, including operating systems, embedded systems, compilers, and game development. The first step in program development is problem definition, where you must clearly understand the problem. This involves identifying inputs, outputs, and constraints. The second step is solution design, or algorithm development. An algorithm is a step-by-step logical procedure to solve a problem, characterized by being clear, finite, correct, and efficient. The third step is flowchart representation, a graphical tool using standard symbols to represent the algorithm visually. Here is an example of a flowchart, illustrating the flow of a program from start to end, including input, process, decision, and output. The fourth step is pseudocode writing. Pseudocode is an informal, English-like representation of the algorithm, focusing on logic to bridge the gap between the algorithm and the final program. The fifth step is coding, where the algorithm is converted into an executable program using a programming language like C, following proper syntax and coding standards. Step 6 is compilation, where the code is translated into machine code, and errors like syntax mistakes are detected. Step 7 is execution, running the compiled program to process inputs and produce output. Step 8 is testing, where the program is checked with various inputs, including normal, boundary, and invalid values, to ensure correctness and reliability. Step 9 is debugging, the process of finding and fixing errors, including syntax, runtime, and logical errors. Step 10 is documentation, which explains how the program works for future users and developers. The final step is maintenance, which is necessary post-deployment for bug fixes, performance improvements, and adapting to new requirements, ensuring the program remains useful. Thank you for watching this video on the basics of C programming.